In my research, we do a lot of repeated measurements, and people are actually confused about that. So I think these questions are actually good. They seem obvious because we're learning them in a class, but you've got all these measurements. They're the same measurement, but they're just doing the same measurement over and over and over. And you see that you get these, it doesn't matter what it's about. There's a scenario there, but it's just a bunch of these different measurements. Why aren't they exactly the same? Well, it might be different environmental conditions. It's a device that's doing something. There might be measurement error. They could actually have some kinds of recording or rounding error that could happen, but the one that's wrong is the physical quantity must have a completely different true value every time it's measured. No, that's not true. It's all the ways we're measuring it that have the effect. And there's small variation in the measurement process. That's true too. Take something like height. Let's say I measure you 3 times for height, but I get slightly different amounts each time. The reason why I get slightly different amounts is you might be slightly slouching one of the times, or the device I'm using has a little bit of like wiggle on it. There's some variation in that, but it's not because your true height has actually changed 3 times. So that's why the physical quantity must have a completely different true value every time it's measured is incorrect. We are going to move to that one, from that one to the next one, which was a problem on, I think it was a histogram problem. So let's go look at that. Oh, by the way, the best answer for this one, I forgot to answer this one. Is this a enumerative study? It's not. In fact, I had just talked to my friend about this. It's because the measurements are viewed as outcomes of an ongoing process, and there's no fixed sampling frame containing all possible measurements. So the rest of these answers are ludicrous. The 8 measurements don't come from the entire population. Every data set's not automatically an enumerative study, and 8 observations are not enough. Like, there's no such thing. So just by default, they're trying to get you to understand what an enumerative study is. So here is data. Again, a disgusting small polymer beads example. And they gave you a table from a histogram. And they asked you first, the first thing you have to do is you have to do the total number of observations. Otherwise, you can't divide by the right thing when you need it. So let's take that. We're going to take the frequency numbers. That's how often the different types of numbers that fall into each one of these buckets. So I'm going to add them all up here. Let's stick this on a calculator. And I get that this thing is equal to 135. So my total number of observations is 135. Can't see my screen, so let me push this up. Total number of observations. So I need this number. And then I'm asked for the proportion that is less than 4 millimeters. So I look at these buckets and I think, which are less than 4 milliliters? Well, millimeters. The buckets that are less than 4 are going to be this bucket here, this bucket here, this bucket here, and this bucket here. They're all less than 4. So I total up those. And I get from that, if I add them all up, this is 81. And the proportion, that's why I needed the 135, which is 0.600. So that's the proportion. The next question, part B, asks for the proportion less than 5 millimeters. Ugh, so it's the same question. I already got the 81 for the 4s. So less than 5 would be up to here. So I'm going to take this 81. I already did the 81. It's up to 4. And I'm going to add in the 24 and the 15. From here, these two. And that's going to give me, oh, I think they want at least 5 too. Let me see. Question. At least 5. So I got it backwards. I couldn't use my old thing. Sorry. Didn't read the question. I was just going to the next question. All right. So they want at least 5. So it's got to include 5. So I have to go back up to this top chart. At least 5 means it's got to be 5 to 5.5. So I'm going to add up these guys here. And so I get 8 plus 4 plus 2 plus 1. And that's going to give me 15. And again, I do need this proportion. So I get 0.111 repeating. And then part C, they ask for a relative frequency histogram. Each frequency is divided by the total first. So how do I make one of these? By hand, I go to each bucket. So I look at the frequency of the first bucket. I got 5 in that first bucket. So the frequency is going to be 5 divided by 135, which is 0.037 approximately. And so if I do this for all of them, I'm going to get this kind of, let me do, so I'm going to do this for each one of them. I'm going to go through and put diameter 2 to 2.5, 2.5 to 3.0, strictly less than, I left out the strictly less than, 3.0 to 3.5, and then I'm going to put the frequencies, and I'm going to get something like this. 0.037, 0.104, 0.200, and so forth. If I plotted that, let's put 0.5 here, so everything's down here. What that's going to look like, it's the first bucket's going to be pretty low, but not very low, right? The first bucket is the first bin. It's going to be somewhere around 0.37. And the next one's going to be a little bit higher. And then it's going to rise up till about 2.59 for the third bin. And then suddenly it gets back to being small and very small. It goes really tiny like this, if you look at the numbers. So I'm going to have you calculate these numbers, but it's going to have a long, small tail because the last numbers, like down at the bottom, like the 6.5 to 7, it's going to look like 0.007, which is so small compared to the very first number I got. So these numbers, because they're so small, you're going to have what we call a longer tail when I graph this little bar chart of frequencies to the right. So we call that positively skewed. Long right tail. Now I'm drawing these manually up here. You can certainly draw them on Excel. It's not that hard to draw them manually. I'm being a little lazy here and not drawing the whole thing. But these numbers on the end, they all, after this 0.2, start to get really small. And I know this, like that's going to make little small hikes here at the end. how do I know it's positive? Well, the definition is the direction of that skew. Because I have a long tail to the right, we call it positively skewed. We call this a density histogram, and let's look at the question that they ask you about. So the density histogram, your height value, how high you're going to go, is equal to the relative frequency divided by the class width. So what I computed earlier was the relative frequency, this 0.037, this relative frequency of my first bucket. My first bucket was 2.0 to 2.5. The size of that bucket is 0.5. Or the width is equal to 0.5. That's that width. So the height of my density plot is going to be 0.037 divided by 0.5. And that's about 0.074. And they just want you to plot that. I think for your WebAssign, you probably have different histograms to choose from, but that's how you probably don't have to do all of them. You can probably just plot a few of them and then see which one matches up. This is your first height, and you'll just plot those in order. All right, so let's look at the questions that are here. How should the shape of the density histogram compare with the relative frequency histogram? Well, the relative frequency and density histograms are going to have the same shape. Only the vertical axis scale changes. And that should be one of our, yep, here we go. There it is right here. They're not going to look different. That's what you should see. I already kind of knew that was going to look that way. And next question is, do we have any more questions? We don't have a question on this. So let's do the last problem because Dr. T is getting tired too. On this problem, they have a 12-mile foot march, and we have the person's time for an early 2-mile segment and for a late 2-mile segment. And the difference would be the late time segment minus the early time segment. And so they generated a histogram for all these participants. So it's just like we did before, the frequency. We would divide by all the observations and then look at the number in each bin. So each of these represents time differences. And so in the time difference where 0 was at the center, it's a weird time difference. The frequency was 175 when you did the division. You do it the same way as we did before. And then now we have some questions about the features of that histogram. So let's look at that. most of the observations are positive. Well, to be positive, it means that the observations you recall were the late time segment minus the early time segment, and this would be the number of things in each bucket. So if we go back and look at the histogram, the time difference, see down here the time difference was negative, but we see that most everything is to the right of 0. So yes, that is correct. That for the most part, I didn't get a time difference that was negative. There was some. And so we don't get all of that. The distribution appears normal. Now, it's got this long tail to the right, just like our other one. To be normal, it had to be symmetric and bell-shaped. And so I'm going to say no on that one. And the next question is that the distribution has a very small spread. That's not true. It goes from below 0 to hundreds of seconds above 0. That's a pretty big range. That's not reasonable. It's not. Is it negative skewed? No, it's positive skewed. My tail is to the right, so it's positively skewed. So the last one's correct. The negative one's incorrect. Small sample size? I don't think so. It's got a large number of observations, I can tell from this. The bars represent the frequencies. The frequencies are pretty high. And so I'm going to go with a larger sample size. So in the next question, again, in WebAssign, you're going to have multiple choice. And here I make you actually calculate something. So how do you, they want a typical value of a time difference. So from the histogram. So if we go to the histogram and look at it, let's go back up and look at it. Most values are right here. So this is 100. This is 0. 50 is probably right here. So like maybe somewhere from here to here, 60 to 100 was like where most things are. So I'm going to take my window to be 60 to 100, approximately, is the center. And the approximate typical value from that history, like, so what we can do is, the median's approximately at 60 seconds. It's kind of hard to see, but it looks like this is kind of where the middle might be. And then from the histogram, we can kind of like generate a approximate answer for that. Like 60 seconds is the median. And the next question asks, what's the proportion that did the last segment more quickly? If they did the last segment more quickly, that means that the answer is going to be negative because the tail part was faster than the first part. So what proportion of the total got it to be, well, those are all your negative stuff. So right here, the frequency was about 60. Right here, the frequency was about looks like I got about, like each one of these chunks is about looking at about 50 out of the total. So we got times the total number of observations. We like the times that were viewed were like the proportion of the histogram lying to the left of 0. So if I just do a quick and dirty